Hey, this little ditty is about the Bohr atom. And it's versus the correct model of the atom. We don't know what the correct model of the atom is. We don't know exactly what's going on. We just kind of have an idea about what's going on. And it's just a model that try to represent what's going on. We don't know exactly what's going on. So let's talk about this Bohr atom and what it meant back in the day and what it still means today. So there's the early model, plum pudding model. We have positive and negative charges throughout. That's not what it is. So yeah, atoms are pretty small, 10 to the 10th for the hydrogen. Light is not as small as that. It's larger than that. Electrons is okay, so we're talking about wavelengths of the electron here is what we're talking about, not the actual size of an electron. We don't have a size of it. Oh, it says wavelengths right there. All right, so there you go. We don't have really a size of an electron, and that's the electron with an energy of 1 eV has that wavelength of a nanometer. And helium atom even smaller than that, because now we're holding on to these. We got an extra proton. We're holding on to those electrons even tighter. We're getting even smaller yet in our atoms. And then this guy Rutherford shot some helium particles into there, into some gold foil and everything, and he found out that pretty much there's not really much in an atom whatsoever, except at the very center. So most everything he shot went right through the middle without interacting with anything. But every so often something went backwards. In other words, you hit something pretty solid every so often, but it wasn't very often at all. And that's where we found out there's something pretty solid in the middle, and that's where a modern idea of that all the mass of an atom is really very densely located right in the middle, which is the nucleus. That's kind of our modern idea of where the nucleus is located, anyways, from this Rutherford scattering. Okay, so that plum pudding model fell through because that's not what happens. So we're going to keep on running through. So the atom is mainly empty space. All the mass is located at the very center in a very small radius, and most everything else. You might say, hey, that's not a big difference in size. That's a flippin' huge difference in size. That's 10,000 times difference. That's a huge difference, those 5 zeros there. So almost all the mass is located in a very small spot right there in the middle, very little on the outside of that. Alrighty, so this scale is way out of whack. The size of this nucleus is way, way, way smaller for those electrons. We don't really know they're in orbit. We don't know what they're doing. There's a probability of where to find those is what we can find, and that's about it. Due to the uncertainty principle, we know about where they are, but we don't know exactly what their momentum is. Once we know about where they are and we try to find out where they are, we can't know what their momentum is. If we know what their momentum is, we don't know where they are, and so forth. We talked about that a little bit the last little thingy. So here we go. So okay, so the classic nuclear atom, not stable electrons or radio. Okay, so the classic thing where the electrons in orbit can't be, because if you have an accelerated electron, well, that makes electromagnetic energy, and that means you're losing energy. Electron, if you're losing energy, that means it's going to spiral into the nucleus, and then you have no more atom anymore. So that can't be happening. So you can't be in a perfect circular orbit, so that can't be true. So that's where we're going to get to go in quantum. We can't be just a planetary orbit. That doesn't work for an atom, for a class in the classical sense. It can't. You can't have a classically orbiting electron, because that violates some classic dynamics of your accelerated electrons losing energy. Well, where do you get the energy from to stay in orbit then? There's a problem there. Alrighty, so photons have momentum. Everything has a wavelength. Even you and I, if we're moving, if we have momentum, we have a wavelength. The uncertainty principle, but we can't know one thing without the other very well. That's a special kind of H. Special kind of H is the H over 2 pi. It's not a big deal. Just cleans things up a little bit. Hey, there's an atom. So you have a positive nucleus. It's very small, very dense on the inside compared to the rest of it. The orbit, the electrons are way the heck out there, way out there compared to the nucleus, 10,000 times the distance out there. And this classical stuff of the electromagnetic, the electron in orbit does not give it a stable orbit. That can happen. So there's a problem with that. So that's why we have the quantum mechanics, to try to explain what's going on with those electrons that they can't be in a normal classical orbit. It doesn't work. So now we're getting into this Bohr model back in the 1913s to describe what's going on. And maybe UFOs can help us with that a little bit. So, so there are some problems with the Bohr model, and some people say it's complete nonsense because you can't circle the nucleus like little planet orbits. There's some assumptions injected into this model that don't really have a basis in physical reality, and maybe UFOs do. But the model does get some things that model what's going on. So there are some things that are right for hydrogen, but not right for all the other atoms out there besides hydrogen. So there's some problems, but they get some things right. So we still kind of use it as a model to show that it's got some merit anyway. Some merit to the thing. So we're going to go kind of quickly through some things. So the Z is a proton number. It's got one. Hydrogen's got one proton. Helium's got two. Lithium's got three, and so on. It's got one electron, since it's got one proton, one electron. Okay, and so the Bohr atom works for hydrogen-like atoms, is what we're trying to say here. It doesn't work for all atoms very well, but for a hydrogen-like, it tends to work pretty well. So one way to get around this classical problem of the circular orbit is to do the de Broglie standing wave. That there's actually a standing wave going on here, that the standing wave, and it doesn't radiate energy the classic way, because you set up a standing wave, because this electron that's moving actually has a wavelength to it, and it has this standing wave orbit to it, that it sits there and doesn't radiate energy in that standing wave there, but it can absorb energy and goes to a different standing wave. But it has to have a certain amount of energy to be standing in that wave. It can only change just different orbits. So we're trying to describe is why we only have certain energy levels in an atom. You can't go from a little more energy to a little more energy to a little more energy. There are quantized limits of energy within the atom, and that's what the Bohr model does. It describes that you can't be in between. An electron can be from one energy level and it can jump to another energy level. It's never in between. There is no in-betweenzs here. You're either here or there, or you go back to here. But even in the jumping, you're never in between. You're only in those certain orbits. Whether you're looking at the classic model and the planetary, which it can't really happen, or if you're looking at these standing wave functions, you're only in between those functions. You're never you're only at those functions. You're never actually in between there. Only certain orbits are allowed to there, and hence that's what the n is. You're at in 1, 2, or 3. This could be a 1, this could be a 2, and it could be a 3, and another level, and another level after that. And there's some other fancy stuff over here. We're not going to get too caught up into all of this stuff in terms of momentum and the r and the distance, but there are only certain allowed distances. Now for AP2 stuff, we're not even going to get too caught up into the exact r's at those certain distances, but what we do have to know, there are only certain allowed orbits is the key. And this is your angular momentum, which is your mv times your r, which is your angular momentum when all the mass is located in one spot. And we're showing that your angular momentum is related to these standing waves, is what it's really related to. But you don't really have, and so the angular momentum is quantized, in fact. But you may or may not get a question on your AP2 about that in terms of the Bohr model. That these angular momentum is quantized in these standing waves according to de Broglie wavelengths there. So the energy is in fact quantized, and not only is the energy quantized, so is the angular momentum. It's possible on your multiple choice questions for that to pop up. So analogy of a particle in a hole here. So talking about your classical mechanics is you can dig a hole and you drop in, you've dropped in the hole, you've got negative energy now. You can drop in a deeper hole, you got more negative energy. Same kind of idea, but the difference between this and classical mechanics is you could be anywhere. If you're digging a hole, you could be any kind of depth. You could have just a ramp here, and you could be at any kind of depth here in this ramp. Well, that's not true in the quantum world. you only have certain steps or quantized steps in the quantum world. You can't be anywhere in this whole. You only have certain quantized steps that you can be at, depending on the atom. And every atom has a different step and different energy levels. All the steps are different per the atom because you have different number of protons and different number of electrons. You have a different step levels and different energy of steps into there. So just like you have, excuse me, different negative mg, but they're only steps in the quantum world. So that's how it's different from the classics, is that classically you can be anywhere here. In the quantum world, you can't be anywhere. Classically, technically, there's only certain steps in here, but the steps are so small, you can't see them. You can't even measure how small the steps are classically. So technically, it actually applies to classically. You just can't tell because the steps are just too small. Alrighty. So now in the quantum world, it's the same idea, but we can now, everything's on such a small scale, we can definitely see the steps, and there's no in-betweens. The ground step is the smallest one you can be in, the lowest energy. But notice you're in the negative hole. So it's always going to be a negative energy, and the energy of 0 is up to here where you have no potential whatsoever because now the electron's no longer attached. So as we go lower, we have a lesser and lesser potential energy because it is a negative as you get to a lower ground state of energy or a deeper hole. And so here is no potential energy, and as we get lower, we're getting less and less potential energy, lower negative number. Okay? So technically you're gaining potential energy, but here you're at no potential energy whatsoever because you're at the 0 here as you're doing work to move this electron away from the thing. Alrighty. So 1 eV of kinetic energy of an electron that has been accelerated through a potential difference of 1 volt. Alrighty, so if you do 1 eV of work on an electron, they say this is Q, would be the charge of 1 electron, it's charge of 1 E, across 1 volt, that's 1 eV of work you did. But remember, if you don't use the E, if you use the charge of 1.6 times 10 to the negative 19th times 1 volt, that's an energy of 1.6 times 10 to the negative 19th joules, which is the same energy as 1 eV. We don't talk about usually joules because it's such a small number. We tend to prefer the eV, but it's the same energy. So in Planck's constant, you got your 6.63. There you go. Or you can take it times the speed of light and stay in the eV in the nanometers and use a 1240. That can save you some time. This can be a time saver if you remember this, but we're not going to use the calculation much, so I wouldn't worry about the 511. They're going to use this a bit here, but we're going to zip through those calculations so fast because you're not going to have to do those calculations for your AP2. Do you know the mass of an electron? 9.11. But so you're going to see that pop up. But as I said, when you get to this hairy stuff like this, we're going to zip through super quick like. And so I don't want you to worry about that, is because we don't have enough time to worry about that because you're not going to see that pop up on your AP2. So we're going to zip through, and all of these scribbles here, we're going to skip through all the scribbles. It only works for the hydrogen atom specifically. So that's not something you're going to have to concern yourself with on your AP2 test. Okay, so energy levels, they're just getting into particular levels of how you find the energy levels with all of this other stuff, the blah, blah, blah. There's your ground state, your 13.6. Okay, you're going to see that pop up again. That's the only thing you need to worry about right now. The radius of the orbit. So if you wanted to find the radius of it, you're not going to have to find the radius of the orbit in your AP2. So let's not be concerned about the radius of the orbit and what it depends on your Z number, your number of protons, and what energy level you are. But that's how you would find that. Alrighty, so there's your radius of your orbit. There's your Bohr radius, depending on what energy level you are and how many protons you have. So if the electron of a hydrogen atom is 207 times heavier, like a muon, the Bohr radius would be 207 times smaller. It's on the bottom there, okay? All right, so the M is electron mass down here, and don't worry about that. You're not going to see that question pop up on your AP2. A single electron is orbiting around a nucleus at a charge of 3. Once again, you're not going to run into this on that big hairy equation there. So we call the charge as that, 13.3. So that's going to be, because it's the squared thing, it's going to be the 9. And like I said, the squared thing, you're not going to have to worry about that one. Alrighty.